Hello everyone and welcome to another recitation video. Today I'm going to solve a few problems from the topic of first law analysis of control volumes. I'm going to cover both steady state flows and devices and unsteady flows. So let's start with problem 1. We have a pipe. The diameter is given 28 centimeters and air enters steadily at 200 kilopascals and 20 degrees Celsius with a velocity of 5 meters per second. We are heating the air inside the pipe, and when it leaves with a pressure of 180 kilopascals and 40 degrees Celsius temperature. Now we are asked to find the volume flow rate at the inlet, the mass flow rate, and the velocity and volume flow rate at the exit. So here is our pipe. Air enters from this side and exits from the other side. We also have an element inside which is heating the air. Now, let's start with part A. So at the entrance, I'm going to show it with I for inlet, and then I'm going to show the exit with O for outlet. So at inlet, what do we have? We have pressure is 200 kilopascals. Temperature is 20 degrees Celsius. And the velocity is 5 meters per second, right? At the exit or outlet, we know that the pressure is 180. Temperature is 40 degrees. We don't know anything about the velocity at the exit. Okay, part A asks for the volume flow rate. So volumetric flow rate, we show it with capital letter V dot, is velocity times cross-section area. Now we are looking for the volumetric flow rate at the inlet. So V dot I is velocity at the inlet, cross-section area of the pipe. Now plug in numbers, we have 5 meters per second times the cross-section area. It's a circle with a diameter of 28 centimeters. So that will be pi d over 2, which is 0.28 over 2 squared. Doing the math, we get that the volumetric flow rate, the inlet, is 0.3 meters cubed per second. So that's part A. You just need to know the equation for the volumetric flow rate and then plug in numbers and you get the final answer. Okay, for part B. For part B, we are asked to find the mass flow rate. Now, mass flow rate, m dot, is density, velocity, cross-section area, or velocity, cross-section area over the specific volume. Just to make sure, I'm going to write a specific volume here. So we know that this is small letter v, and this is capital letter V showing the velocity. Okay, but how can we find this specific volume? We are going to use the ideal gas equation here. So ideal gas equation says pressure, specific volume, is equal to gas constant temperature. So specific volume will be gas constant times temperature over the pressure. So at the inlet, if I plug in the numbers that I have at the inlet, specific volume of air is air gas constant. The value for air gas constant is 0.287 kilojoules per kilogram Kelvin. Plug that in here, 0.287 times. Now, temperature in the inlet is 20 degrees Celsius, but we need to plug in Kelvin. So that will be 293 Kelvin over the pressure is 200 kilopascals. do the math, and we get that the specific volume, the inlet, is 0.0204 meters cubed per kilogram. Now I can say m dot is velocity cross-section area over specific volume. Now velocity cross-section area, we already know it's the volumetric flow rate. Okay, so volumetric flow rate at the entrance or at the inlet, we already know is 0.3, and the specific volume is 0.4204, which will give us m dot is 0.7136 kilograms per second. So basically, in order to find the density or specific volume of the gas, we use the ideal gas equation and then plug the numbers into the equation for mass flow rate. Okay, so for part C, we are asked to find the velocity and the volume flow rate at the exit. Now, the conservation of mass says that mass or rate of mass or mass flow rate coming in is equal to the mass flow rate going out. Because it's a steady state flow, so no mass is being stored in the system. And it's a single stream, it has only one entrance and one exit. So whatever comes in, m dot I, is equal to whatever goes out, m dot O. We also know that m dot is velocity cross-section area over a specific volume, right? So I'm going to use this equation and plug it back into a conservation of mass. I'll get velocity at the inlet, cross-section area of the inlet over a specific volume of the inlet is equal to the velocity of the outlet, cross-section area of the outlet, the specific volume of the outlet. Now, cross-section area of the pipe does not change. Area at the outlet and area of the inlet are the same because it's a pipe and the area is not changing. With that in mind, we can cross both cross-section areas, and then we get that the velocity outlet is specific volume at the outlet over specific volume of the inlet times velocity of the inlet. I need to find the ratio of a specific volume of the outlet to the specific volume of the inlet. So ideal gas equation for air states that pressure at the inlet, specific volume of the inlet, over the temperature of the inlet is equal to the pressure of the outlet, specific volume of the outlet, temperature of the outlet. Now I can play with this equation and get that specific volume of the outlet over the specific volume of the inlet is actually temperature of the outlet, pressure of the inlet, over temperature of the inlet, pressure of the outlet, right? So I can plug in numbers here and find a number for specific volume outlet over specific volume inlet. So let's do it. I get that specific volume outlet over specific volume inlet is, now temperatures need to be in Kelvin. Outlet is 40 degrees centigrade. Into Kelvin, it goes to 313 times pressure inlet, 200, over temperature of the inlet, 293 times the pressure of the outlet, 180. This gives you 1.187. So I want to plug it here and say the velocity at the exit is 1.187 times the velocity at the inlet, which is 5. This gives you 5.93 meters per second. So we found the velocity at the outlet. All we need to do is find the volume flow rate at the exit. Now, volumetric flow rate at the exit is volume at the exit, area at the exit, which, if we plug in numbers, 5.93 meters per second for the exit velocity, and pi times diameter squared over 4 for the area, we get that the volumetric flow rate at the outlet is 0.3558 meters cubed per second. Okay, so basically for part C, again, we used and manipulated the ideal gas equation here to find the ratio of specific volume in the outlet and specific volume at the inlet. Then we plugged in what we got into this equation, and then the rest is just doing some calculations. Okay, problem 2. We have steam entering a nozzle at 5 megapascals and 400 degrees Celsius steadily, meaning that this is a steady state problem. The velocity at the inlet is given 80 meters per second. The steam exits the nozzle at 2 megapascals of pressure and 300 degrees Celsius. The area of the inlet is given 50 centimeters squared. We also know that some heat is lost during this process. We are asked to find the mass flow rate, the exit velocity, and the exit area of the nozzle. Okay, so what we have is a nozzle like this. Steam enters from here and exits from there. So this is the inlet and this is the outlet. The area of the entrance of the nozzle is given 50 centimeters squared. All right, so let's start with part A. So at the entrance, we know that our pressure is 5 megapascals and our temperature is 400 degrees Celsius. Now, what about the exit? At the outlet, we know that our pressure is 2 megapascals and our temperature is 300 degrees Celsius. Okay? Now, mass flow rate. In order to find the mass flow rate, remember mass flow rate, m dot, is density times velocity times cross-section area, or velocity cross-section area over specific volume. We know the cross-section area at the inlet. We also know the velocity at the inlet. We only need to find the specific volume at the inlet so that we can use everything in this equation to find the mass flow rate. Specific volume of the inlet. So we need to check the tables first to pinpoint the state or steam when it enters the nozzle. So if you check the tables for 5 megapascals, you would see that the saturation temperature is 263.94 degrees Celsius. And because 400 degrees is greater than 263.94, then we know that we are in the superheated region. So at the inlet, we are dealing with a superheated steam. So we go check the tables for superheated steam at 5 megapascals and 400 degrees Celsius, and we get that the specific volume at the inlet is 0.05784 meters cubed per kilogram. Now that we have the specific volume at the inlet, we can use the equation to find mass flow rate. So m dot is velocity at the entrance is given. It's 80 meters per second times the cross-section area is 50 centimeters squared. Now, 50 centimeters squared is 50 times 10 to minus 4 meters squared. Remember, we need to keep the units consistent, over the specific volume, which we read from the tables, 0.05784. Do the math, and you get that the mass flow rate is 6.915 kilograms per second. So basically, the point of this problem is for you to check the tables. First, pinpoint the state of the steam at the entrance, and then check the table, find the specific volume, and then plug it back into your mass flow rate equation. And the rest is just doing calculations. Okay, for part B, we are asked to find the exit velocity of steam. Now, the first equation that comes to mind is the conservation of mass, right? So let's write it. We know that whatever is coming in is equal to whatever is going out because it's a steady flow and a single stream steady flow. So whatever is coming in is equal to whatever is going out. Now write it down in the equation form. We get that velocity entrance cross-section area of the entrance over specific volume of the entrance is equal to velocity outlet cross-section area of the outlet, specific volume of the outlet. On the right-hand side, these two are both unknown. We don't know the velocity, we don't know the cross-section area. We can find a specific volume at the outlet using the state of the steam when it leaves this nozzle, but anyway, even if we know that, there are two unknowns here in this equation, and so it's not really helping us right now. So let's change our approach. I'm going to write down the first law here and see if that can help us. So you know that Q dot net, I'm dropping the subscript net just to make things simple, but you should know that this is Q dot net minus W dot net plus all the energy that the fluid is bringing in minus all the energy that the fluid is taking out is equal to 0. The right-hand side of this equation is 0 because we are talking about steady state flow. Theta, or the energy of a moving fluid, just to refresh your minds, is the enthalpy plus kinetic energy plus potential energy of the fluid. Okay? Now in this particular problem, 120 kilojoules per second of heat is lost. We also know that we can neglect the change of potential energy. So, because there is no change of elevation anywhere, so we can drop this term. And also, this diffuser does not involve any kind of work. There is no boundary work, there is no mechanical work, no electric work, no nothing. So W dot also drops. We get that Q dot is equal to, now, earlier we developed that mass flow enter is equal to mass flow rate exit. So I can say Q dot is equal to mass flow rate times HO minus HI plus velocity O squared minus velocity I squared over 2. I expanded the theta term and moved these two guys to the right-hand side of the equation. Okay, so we need to find enthalpy at the outlet and enthalpy at the entrance. So at the entrance, we already know that we are dealing with a superheated gas, superheated steam. So I can just read the enthalpy from the tables. H of I is 3,196.7 kilojoules per kilograms from the tables. At the outlet, if we go check, we'll see that the temperature at the outlet at 300 degrees is greater than the saturation temperature of water at 2 megapascals, which is 212 degrees. So again, at the outlet, we are still dealing with superheated steam. And then we can use the tables to find that H of O is 3,024.2 kilojoules per kilogram. Okay, so I found both of these. Now I can plug in everything here. Now, Q dot net, the only heat transfer involved in this problem is 120 kilojoules per second heat loss. So minus 120 kilojoules is equal to mass flow rate. We know it from part A is 6.915 times, now h of exit, 3024.2 minus h of entrance, 3196.7 plus unknown velocity of the outlet squared minus the velocity inlet is 80, so 80 squared over 2. Now, you need to pay attention here. This is in kilojoules per seconds or kilowatts. This is in kilojoules per kilograms, but this term is in joules per kilogram, right? So as you can see, there is a unit difference or inconsistency between these two terms that we are adding. So we need to address that. In order to solve this, I'm going to change this term to kilojoules per kilogram. How? I'm going to divide it by 1,000. If I do that, the unit changes to kilojoules per kilogram. Now let's continue. So from here, if we do the math, we get that the velocity at the exit is 562.75 meters per second. Okay, so the most important part of this problem was for you to convert the unit here and make both units consistent. The rest is just plug in numbers. Finally, for part C, we are asked to find the exit area of the nozzle. We already know the velocity at the exit. We also know the mass flow rate throughout the diffuser. We can use those to our advantage. So mass flow rate is velocity cross-section area over specific volume. So cross-section area will be mass flow rate times specific volume at the outlet over velocity at the outlet. So what is the specific volume at the outlet? We know that we are dealing with a superheated steam at the outlet, so I can read the specific volume from the superheated table, 0.12551 meters cubed per kilogram. Now I can plug in all my numbers and find the area of the outlet. So area is, m dot is 6.915 times the specific volume, 0.12551, over the velocity. From part B, we know is 562.75. Do the math. You get that the area at the exit is 0.00154 meters squared, or 15.4 centimeters squared. Again, we use the mass flow rate equation. We found the specific volume using the tables, and then the rest is just plug-in numbers. All right, problem 3. We have an adiabatic turbine. Steam flows through it steadily, so steady state. The inlet condition of the steam is given 10 megapascals pressure, 450 degrees Celsius temperature, and 80 meters per second velocity. The exit conditions are also given 10 kilopascals pressure, quality is 92%, and the velocity is 50 meters per second. The flow rate is 12 kilograms per second, and we are asked to find the change in kinetic energy, the power output, and the turbine inlet area. Let's draw a schematic of our problem. This is our turbine. We have an entrance here, and then we have an exit here. M dot is 12 kilograms per second. Now, what do we know? We know that at the inlet, pressure of 10 megapascals, temperature of 450 degrees, and a velocity of 80 meters per second. And at the outlet, pressure is 10 kilopascals, quality is 92%, and the velocity is 50 meters per second. So these are the things that we know. So let's get started with part A, the change in kinetic energy. So what we're actually looking for is delta KE, small letters, which is velocity squared at the outlet minus velocity squared the inlet over 2. So you plug in numbers and we get delta KE is 50 squared minus 80 squared over 2. Do the math and you get that delta KE is minus 1.95 kilojoules per kilogram. Which means that throughout this process, throughout this turbine, every kilogram of steam loses roughly minus 2 kilojoules of energy, kinetic energy. So let's go to part B. Part B, we are asked to find the power output. So this gives us a clue that we need to use the first law equation. So Q dot net minus W dot net plus all the energy coming in with the flow minus all the energy going out with the flow is 0. Now the problem specifically states that we are dealing with an adiabatic turbine. That means no heat transfer, so Q is gone. We can also neglect the potential energy. So no GZ terms. With that in mind, we can continue simplifying this equation. I'll get minus W dot is equal to, now remember this is a single stream steady state device, so whatever's coming in is equal to whatever's going out. I'm just going to label it mass flow rate for simplicity. So this will be mass flow rate times, again, enthalpy at the exit minus enthalpy in the entrance plus velocity exit squared minus velocity inlet squared over 2. I already know this term. This is the change of kinetic energy here. All I need to do is find the enthalpy at the outlet and the enthalpy at the inlet, and I should be good. Okay, so at the entrance, pressure is 10 megapascals and temperature is 450 degrees. Again, just like previous problems, if we check the tables, we will see that we are dealing with a superheated steam. So jump to the superheated tables and read the value for H of I, or the enthalpy. So H of I is 3097.5 kilojoules per kilogram. Now at the outlet, we are dealing with the pressure of 10 kilopascals and a quality of 92%. Now quality should give you the idea that we are dealing with a saturated mixture. So I'm going to check the tables again. This time I'm going to read both H of F and H of Fg at the pressure of 10 kilopascals. Okay, so if I do that, H of F is 191.81, H of Fg is 2392.1, both in kilojoules per kilogram. And then I can use the quality equation saying H of O is H of F plus quality H of Fg, and then plug numbers and get that H of O is actually 2392.54 kilojoules per kilogram. Okay, now I have everything. I can plug these numbers back into this equation. Let's do it. Okay, so minus W dot will be, M dot is 12 kilograms per second from here, times H of O, 2392.54, minus H of I, 3097.5, minus this term here, we already know is minus 1.95, so 1.95. Then do some math, and we get that W dot is 8,482.9 kilowatts, which is about 8.5 megawatts worth of power. So our turbine here is producing 8.5 megawatts of power. Now, there is something that you need to pay attention to. The difference of enthalpies in this equation is about 704.95 kilojoules per kilogram, while the difference of kinetic energy is 1.95 kilojoules per kilogram. Now, as you can see, the change of kinetic energy can be neglected when compared to the change of the enthalpy of the steam. Okay, so basically, the power that the turbine produces is not from the change of kinetic energy of the flow, but rather the change of enthalpy of the flow. Neglecting kinetic energy is a valid assumption when dealing with steam turbines. Okay, so for part C, we are asked to find the turbine inlet area. So again, go back to the mass flow rate equation. M dot is density, velocity, cross-section area, or velocity, cross-section area over specific volume. Now, I know everything except the cross-section area at the inlet, so M dot is velocity inlet, cross-section area inlet, over specific volume of the inlet. So I know this velocity at the inlet, I know the mass flow rate, the cross-section area is in question, specific volume I can read from the tables. So if I do that and use the tables, I know that at the inlet we are dealing with a superheated steam. So I go check the tables for the pressure of 10 megapascals and the temperature of 450 degrees, and I read that the specific volume of the steam is 0.026436 meters cubed per kilogram. Okay, now I can plug everything back and find the area. So the area at the inlet is mass flow rate times the specific volume over the velocity. 12 times 0.026436 over the velocity, which is 80 meters per second. You do the math, you get that the cross-section area is 0.00396 meters squared, which is 39.6 centimeters squared. Okay, problem 4. We have steam entering an adiabatic turbine. Again, at the inlet, the pressure is 8 megapascals and the temperature is 500 degrees Celsius. The flow rate is also given 3 kilograms per second. It leaves the turbine at 20 kilopascals. Now, if the power output of the turbine is 2.5 megawatts, we are asked to find the temperature of the steam leaving the turbine. We can also neglect any kinetic energy changes. So again, we are dealing with a turbine, inlet, and an outlet here. Now, what do we know? We know that at the inlet, it is always useful to list all you know, 8 megapascals, and temperature is also known, 500 degrees Celsius. At the outlet, pressure is 20 kilopascals, and we are asked to find the temperature. I know the power output, and knowing the power output or heat transfer or anything power related should give you a hint that you need to use the first law equation. So let's do that. So if I write down the first law, I'll get Q dot net minus W dot net plus the energy coming in with the steam minus the energy going out with the steam is equal to 0. Now theta, or the energy of a moving fluid, we know that it's enthalpy plus the kinetic energy plus the potential energy. Now in this problem, we can neglect both potential and kinetic energies. So theta reduces to enthalpy alone. The problem specifically says that the turbine is adiabatic. So Q goes out. We are left with the power output. Now, power output means that our control volume is actually doing work. You need to remember that in this equation, W dot net is actually W dot out minus W dot in. Now, there is no work done on the system, so this guy is 0. And we have the W dot out, which is 2.5 megawatts, or 2.5 times 10 to 3 kilowatts. Okay, now plug these things back up, and we get minus 2500 is equal to, and mass flow rate is already given, 3 kilograms per second, times h of exit minus h of entrance. Okay, so we don't know the h of exit because we only know the pressure and nothing else, but we can find the h at the entrance because we know two independent intensive properties at the inlet. So let's check the tables. So if I check the tables at the entrance, I will see that we are dealing with a superheated steam because 500 degrees Celsius temperature is greater than the saturation temperature at 8 megapascals. So I go to the superheated tables and read that H of I is actually 3,399.5 kilojoules per kilogram. Now let's plug this number here. If I do and then do the math, I get that the enthalpy of the exit is 2,566.17 kilojoules per kilogram. So now I have the enthalpy at the exit. I also have the pressure at the exit. Using two independent intensive properties, I should be able to find all the other properties. So let's do it. At the pressure of 20 kilopascals, I'm going to read both H of F and H of G. So H of F from the tables is 251.42. H of G is 2,608.9, both in kilojoules per kilogram. Now, for those who don't remember what HF and HG represent, H of F is the enthalpy of saturated liquid, and H of G is the enthalpy of saturated vapor at the pressure of 20 kilopascals. Now, doing a comparison, I get that the enthalpy that I have is larger than the enthalpy of saturated liquid, but it's smaller than the enthalpy of a saturated vapor. This means we are dealing with a saturated mixture. Now, in a saturated mixture zone, the temperature is a function of pressure. So the temperature of the outlet is the saturation temperature at the pressure of 20 kilopascals, and you need to use the tables to read it. It will be 60.06 degrees Celsius. So basically, we found the enthalpy at the outlet using the first law equation. Then I checked that enthalpy with the enthalpy of saturated liquid and saturated vapor at the same pressure. I found that my enthalpy is between these two values, so we are dealing with a saturated mixture. We are inside the dome. Inside the dome, in the saturated mixture zone, temperature and pressure are functions of each other. So the temperature is the saturation temperature at the pressure of 20 kilopascals, which is 60 degrees Celsius. Okay, problem 5. We have a compressor, air enters it at 100 kilopascals pressure and 25 degrees Celsius, and the velocity at the entrance is negligible, very low velocity. The exit conditions are given also 1 megapascals pressure and 347 degrees Celsius temperature. Velocity this time is given 90 meters per second. The compressor is cooled down with a rate of 1500 kilojoules per minute, and the power input of the compressor is also given 250 kilowatts. We are asked to find the mass flow rate of air inside this compressor. So let's get to it. First, a schematic. So this is the compressor, right? This is the inlet, and this is the outlet. We are losing heat with a rate of 1500 kilojoules per minute. And we are also introducing work into the system with a rate of 250 kilowatts. Now let's see what we know. At the inlet, I know the pressure and temperature, 100 kilopascals and 25 degrees Celsius. At the outlet, I also know the pressure, 1 megapascals, and the temperature, 347 degrees Celsius. All right, I need to change the unit for the Q loss because it's in kilojoules per minute, which is not very useful for us. So let's start with that. So Q dot out is 1500 kilojoules per minute. I want this to be in kilojoules per seconds or kilowatts. So in order to achieve that, I'm going to multiply this by 1 minute over 60 seconds. That will give me 25 kilowatts. Now this is a unit that I can work with. So the first law states that Q dot net minus W dot net plus everything that the flow brings in minus everything that the flow takes out is 0. So Q dot minus W dot is, now this is a steady state single stream device, so m dot I is equal to m dot out based on the conservation of mass. So it will be m dot times HO minus HI plus velocity out squared minus velocity in squared over 2. Now the problem specifically states that we are dealing with a very low velocity at the entrance. So I can neglect this term. So Q dot is minus 25 kilowatts. And W dot is, we have some work done on the system. So the W dot net is minus 250 kilowatts. The minus sign shows that the work is done on the system. Plug in these guys back here, you get minus 25 plus 250 is equal to our unknown m dot times, we are dealing with air, so for delta H, we can use the equation, delta H is Cp delta T. So that's what we are going to use here. Cp of air, temperature of the outlet minus temperature of the inlet plus 90 squared over 2. Now, again, we have the same problem that we had a couple of problems ago. This guy gives you kilojoules, whereas this guy is giving you joules. We need to have them in the same unit. So I'm going to divide this by 1,000 so that this will be kilojoules as well. Okay, so I get 225 on this side is equal to m dot. Now Cp of air is 1.005 kilojoules per kilogram Kelvin. The temperature at the exit is 347 minus the temperature at the entrance is 25 degrees Celsius plus 90 squared over 2 times 1,000. Now, if you do the math, you will get 0.686 kilograms per second. Again, the difference between the change of kinetic energy and the change of enthalpy of your gas is too much, and it is safe to neglect the kinetic energy here in comparison to the change of enthalpy of the gas. Okay, problem 6. We have refrigerant R134A. It's going through a throttling valve. Before the throttling valve, it's saturated liquid at 700 kilopascals. And after the throttling valve, the pressure has dropped to 160 kilopascals. We are asked to find the temperature drop during this process and the final specific volume of the refrigerant. Now we are dealing with a new substance, R134A. I have posted the link to the property tables of R134A. It's from Chengel's book again. Make sure to check it down in the description below. We are going to use those tables every time we deal with refrigerant R134A. Now, a throttling valve is a very curious device. All you need to know about it is that enthalpy is constant across the throttling valve and the pressure drops. So with that known, we can say that if this is our throttling valve, this is going in and this is going out, I can say that the enthalpy at the exit is equal to the enthalpy at the inlet. Now at the inlet, I know that I'm dealing with saturated liquid at the pressure of 700 kilopascals. And at the outlet, I'm dealing with the pressure of 160 kilopascals. Okay, I don't know anything else. I can find the enthalpy at the entrance using the state at the entrance. So let's go check the tables. If you do, you will see that enthalpy at the entrance is actually the enthalpy of saturated liquid at the pressure of 700 kilopascals, which is 88.82 kilojoules per kilogram. Now, if I plug in this equation, I get that the enthalpy at the exit is also 88.82 kilojoules per kilogram. Now, I have the enthalpy at the exit, I have the pressure at the exit, but I'm not sure what my state is. So I need to check the tables again. This time, I'm going to check the tables for the pressure of 160 kilopascals. So let's go to the tables for the pressure of 160. I'm going to read both H of F and H of G at this pressure. So H of F is 31.21, while H of G is 241.11, both in kilojoules per kilogram. Now do a simple comparison and you will see that the enthalpy at the exit is larger than the H of F, but it's smaller than H of G. This means that we are dealing with a saturated mixture. When dealing with saturated mixture, the temperature of the mix is equal to the saturation temperature at the given pressure. So T at the exit is the saturation temperature of the pressure 160 kilopascals, and if you read it from the tables, it's minus 15.6 degrees Celsius. So I found the temperature at the exit. Now, at the entrance, I know that the pressure is 700 kilopascals, and I'm dealing with a saturated liquid. So here, the temperature at the entrance is also the saturation temperature at 700 kilopascals. Now, check the tables again, and you will see that the temperature here is 26.69 degrees Celsius. Now, the change of temperature, because the problem asks for the temperature drop, is going to be temperature at the inlet minus temperature of the outlet. Plug in numbers, you get 42.29 degrees Celsius temperature drop. It drops from 26 to minus 15. Now the problem also asks for the final specific volume of the refrigerant, so let's get to that. Okay, so at the exit, I know the pressure and the enthalpy. I also know that I'm in the saturation dome, so I'm in the mixture zone and I have quality. So first I need to find the quality and then use that to find a specific volume. Now quality is enthalpy at the exit minus enthalpy of the saturated liquid at set pressure over the enthalpy of saturated vapor minus enthalpy of saturated liquid at the set pressure. So I'm going to plug in numbers. I get 88.82 minus 31.21 over 241.11 minus 31.21. Now do the math and we get that the quality at the outlet is 0.274. Our refrigerant is experiencing phase change during the throttling process. Now I'm asked to find a specific volume. In order to do that, I will need the specific volume of saturated liquid and a specific volume of saturated vapor at the pressure of 160 kilopascals, because that's the pressure of the outlet. So check the tables again. Specific volume of saturated liquid is 0.307437, and for saturated steam is 0.12348, both in meters cubed per kilogram. Now the specific volume at the exit is 1 minus quality exit, specific volume of liquid, plus the quality of the exit, specific volume of saturated vapor. Plug in numbers, and we get that the final specific volume is 0.03437 meters cubed per kilogram. So the only trick to this problem was that a throttling valve is an enthalpy constant process. The enthalpy before and after the valve are the same. The rest is just using the tables and manipulating the data that we have. Okay, problem 7. We have a mixing chamber. A hot water stream is entering with 80 degrees Celsius with a mass flow rate of 0.5 kilograms per second. And a stream of cold water also enters with a temperature of 20 degrees Celsius. We don't know its mass flow rate. We know that the final mass flow going out of the mixing chamber has a temperature of 45 degrees Celsius. The problem says that all the flows, all the streams have the pressure of 250 kilopascals, and we are asked to find the mass flow rate of the cold stream. So a schematic of the problem looks like this. Something like this. This will be the exit. This will be one of the entrances and this will be the other. So hot water is entering from here, from the top, 80 degrees Celsius, and the mass flow rate is also 0.5 kilograms per second. Cold flow is entering with 20 degrees Celsius. Mass flow rate is not known. And the mixed water exits with 45 degrees Celsius from here. We also don't know the mass flow rate. So first things first is we are going to check the conservation of mass. It says that all the streams coming in are equal to all the streams going out. Okay, so our streams coming in is the m dot of hot water plus the m dot of cold water, and what goes out is the m dot going out. So this is the equation that we get from the conservation of mass. We know a value for m dot h, but we don't know anything about m dot c. So let's keep it like this for now. Then I'm going to write the first law. So q dot net minus w dot net plus all the energies coming in minus all the energies going out is 0. Now we are dealing with a mixing chamber, Now, a very good assumption for mixing chambers is that they are usually well insulated, and this problem does not talk about any sort of heat transfers, so it's a good bet to assume that there is no heat transfer involved. Also, in a mixing chamber, there is no work involved either. So we are left with m dot h, enthalpy of H, plus m dot C, enthalpy of C, is equal to m dot out, enthalpy of out. Now, H means the hot stream, C means the cold stream, and O is the exit or outlet here. Also, I am neglecting any change in kinetic energies and any change in potential energies. That's why theta reduces to enthalpy. Okay, now I can plug in the equation that I got from the conservation of mass into the first law. Let's do it. If I do, I get that m dot h, enthalpy of H, plus m dot cold, enthalpy of cold, is equal to m dot h plus m dot cold times enthalpy of the outlet. Play with this equation a bit more, and you get that the m dot cold is enthalpy hot minus enthalpy of the exit, or enthalpy exit minus enthalpy C, or cold, times m dot h. So all I need to do is find these individual enthalpies. Now first let's check the tables. The saturation temperature for the pressure of 250 kilopascals is 127.41 degrees Celsius. And we know it from the table. Now all these three streams have temperatures smaller than 127.41 degrees Celsius. So all three streams are compressed liquids. So let me write it here. Now with that in mind, we know that enthalpy of a compressed liquid can be approximated using this equation. So the enthalpy of a compressed liquid is equal to the enthalpy of saturated liquid at the temperature given plus the specific volume of the saturated liquid at the set temperature times the pressure of your compressed liquid minus the saturation pressure of the temperature that you have. Okay, now all other properties can be approximated with the same property at saturated liquid with the same at the given temperature, but for enthalpy it is usually suggested to use this equation to approximate better. Now using this equation, I can approximate the enthalpy at all these three streams. So for example, the enthalpy of the hot stream is going to be the enthalpy of saturated liquid at 80 degrees Celsius plus the specific volume of saturated liquid at 80 degrees Celsius times the pressure of the stream, which is 250, minus the pressure, the saturation pressure of 80 degrees Celsius. Now, if I check the tables and plug in numbers, I get that enthalpy of the hot stream is 335.2 plus 29 times 250 minus 47.16, which is 335.23 kilojoules per kilogram. Now, we can do the same for the other two streams as well. Now, I didn't write this equation for each tree individually, but you get the idea. For the cold, for example, for the cold stream, you need to go find the H of F at the temperature of the cold, which is 20 degrees. That will be 83. then check the specific volume at 20 for saturated liquid, and then check the saturation pressure for the temperature of 20 degrees. For the outlet stream as well, find the enthalpy of the saturated liquid at the temperature of 45, find the specific volume of saturated liquid at 45 degrees Celsius, and then find the saturation pressure for the temperature of 45 degrees Celsius. And then plug in everything in these equations and find the enthalpies. Now that I have these three enthalpies, I can plug them back into the equation that we had in the previous page and find the mass flow rate. Now the equation that we had was m dot c is enthalpy of hot stream minus enthalpy of outlet stream over enthalpy of outlet stream minus enthalpy of cold stream times m dot of hot stream. Now plug in numbers, I get m dot c is 335.23 minus 188.68 over 188.68 minus 84.16 times 0.5. This gives me mass flow rate of the cold stream is 0.7 kilograms per second. Okay, problem 8. We are dealing with a heat exchanger. Steam enters a condenser with a pressure of 20 kilopascals and a quality of 95%. Mass flow rate is also given. It is cooled down in this condenser by a water flow from a nearby river. To prevent thermal pollution, the river water temperature is not allowed to rise above 10 degrees Celsius. Now, if the steam leaves the condenser as saturated liquid, what is the mass flow rate of cooling water? So basically, we are dealing with a heat exchanger. We have steam going through a pipe like this and losing heat to river going through a pipe like this. Now steam is entering here and exiting at 20 kilopascals, while the water enters and exits from here, and it enters with the temperature of the river, and it exits with a temperature of river plus 10 degrees Celsius, because that's the highest temperature rise allowed. So what's happening is that steam is losing heat to the river water. So we have two different systems inside this heat exchanger that we need to analyze. So one system is the steam inside this pipe. The other control volume is the river. So we have the green control volume and the orange control volume. And what connects them is the Q, or heat transfer or heat interaction between steam and river. So let's start with analyzing the green control volume for steam. So for steam, what do we know? We know that Q dot minus W dot plus everything the steam brings in minus everything the steam takes out is equal to 0. I can simplify this equation into Q dot minus W dot is equal to mass flow rate times H of exit minus H of entrance. We've done this a few times so far, so you know that if we neglect kinetic and potential energies, theta reduces to enthalpy, and from the conservation of mass, because this is a simple stream pipe, mass flow rate of the exit and mass flow rate of the entrance are equal. So considering all that, we get the final equation in the form of Q dot minus W dot is m dot times enthalpy of the exit minus enthalpy of the entrance. Now inside this pipe, there's no work involved. I can drop W. I need to find m dot first. It is given as 20,000 kilograms per hour. But this is not useful for me. I want it to be in kilograms per second. So I'm going to multiply it by 1 hour over 3,600 seconds. If I do that, I get that m dot is 5.56 kilograms per second. So I found m dot in a more usable unit. Now I need to find the enthalpy at the entrance and the enthalpy at the exit. So let's start with the entrance. At the entrance, what do I know? I know that the pressure is 20 kilopascals. Quality is 95%. Now, quality at the entrance means that we are dealing with a saturated mixture. So I'm going to read the tables and read H of F and H of Fg at the pressure of 20 kilopascals. H of F is 251.42 and H of Fg is 2357.5, both in kilojoules per kilogram. Now I can use the quality equation. I can say H at the entrance is H of F plus quality times H of Fg. H of entrance will be 251.42 plus 0.95 times 2357.5, which gives me enthalpy at the entrance is 2491.4 kilojoules per kilogram. Okay, I found H of I. How about H of O? Now the problem specifically states that steam leaves the condenser, leaves the heat exchanger as saturated liquid. So H of O is actually H of F at 20 kilopascals. We already have it here. This is H of O. So I have both H of I and H of O. Let's plug them into our first law equation. So Q dot is 5.56 my mass flow rate times 251.42 minus 2491.4. Now you do the math, you get that Q dot is minus 12,452.315 kilowatts. So the minus sign shows that steam is losing heat. Now all this heat that the steam is losing goes into the river. So when we are dealing with the orange control volume, we are going to change the sign for the heat. So for river stream, or the orange control volume, again, let's write down the first law. I get Q dot net minus W dot net. I'm just going to write the simplified equation is mass flow rate of the river times HO minus HI of the river. So this is I of the river and this is O of the river. Just like steam, there is no work involved in the river, so W dot can be dropped. Now Q dot, as I said, all the heat that the steam is losing is gained by the river. 12,452 kilowatts is my unknown m dot of the river times delta enthalpy of river water. Now here's a trick that we are going to use a lot in thermo. Now the river water probably is in atmospheric pressure, and we don't know much about it, but we know that it's a liquid, and we can treat it as a liquid. Delta H, or the change of enthalpy of liquids, can be approximated by the equation C delta T. Remember that? So for the water inside the orange control volume, instead of reading from the tables, because I don't have any temperatures to go use the tables, I can just use C delta T. Now C for water at pressure, at atmospheric pressure and the temperature range that we usually work with is about 4.2 kilojoules per kilogram Kelvin. You can read it from tables, property tables, or you can just memorize it. C of water is 4.2 kilojoules per kilogram Kelvin. Now with that known, I can say 12,452 is equal to my unknown mass flow rate of river times 4.2 times temperature at the exit is temperature of the river plus 10. Temperature at the entrance is temperature of river. These two cancel each other, and I get 42 m dot. Now, if I do the math, I get that the m dot of river is 296.48 kilograms per second. So if we want to keep the temperature rise of the river limited to 10 degrees Celsius, we need to provide a mass flow rate of about 300 kilograms per second into our heat exchanger, into our condenser. Okay, problem 9. We are dealing with another heat exchanger. Saturated steam at 40 degrees Celsius condenses on the outside of a thin horizontal copper tube by cooling water that enters the tube at 25 degrees with an average velocity of 2 meters per second and leaves at 35 degrees. We are asked to find the condensation rate of steam. So just to have a general idea of what's going on, I'm going to draw a schematic here. So we have a pipe like this where water is flowing, cold water is flowing from right to left, steam is flowing across the tube like this, and then it condenses and turns into liquid drops like this. Okay, so again, we are dealing with a heat exchanger. In a heat exchanger, it's usually advised to take separate control volumes for separate fluids. Here, steam is one control volume. The cooling water inside the pipe is another control volume. For the steam, if we write down the first law, we get that Q dot net minus W dot net is equal to m dot of the steam times the change of enthalpy, H of O minus H of I. Now, what is H of O and H of I in this particular problem? Steam enters as saturated steam. Now, what are H of O and H of I in this particular problem? Steam enters as saturated vapor, right? So H of I is H of G, or saturated vapor, at the temperature of 40 degrees Celsius. It then leaves at saturated liquid because it has condensed, right? So H of O is H of F, or saturated liquid, at the same temperature, 40 degrees. No work is involved in this problem, so I can drop this term. And I'm left with Q dot is m dot times, now I need to read H of F and H of G from the table. I can play with this equation a bit more. It will be minus m dot H of G minus H of F. Now, H of G minus H of F is H of Fg. So this is minus m dot H of Fg. So we have already heard that the H of Fg is called the latent heat of phase change or vaporization. Here you can see that that's actually true. So Q dot of the steam is going to be minus m dot H of Fg. I can read the H of Fg from the tables for 40 degrees Celsius, and I'll end up with minus m dot times 2406. So Q dot is minus 2406 times m dot. Now the minus sign shows that steam is losing heat. Now we can derive a very important conclusion from this equation, and that is at the constant pressure, H of Fg represents the energy required for phase change. Okay, we had saturated steam or saturated vapor, and it condensed to saturated liquid. The amount of energy that we got from this system is H of Fg. Similarly, if we had saturated liquid and we wanted to turn it into saturated steam, we had to introduce H of Fg amount of energy in order to achieve that. Okay, so we cannot proceed any further for steam. Let's start writing equations for the cooling water. So for the cooling water, I can write down the first law of thermodynamics again. It's Q dot minus W dot is equal to mass dot of the cooling water. I'm showing it with M dot C. Again, HO minus HI for the cooling water, or M dot C delta H. From the previous problem, we know that we can approximate the delta H of the liquid water, as CTO minus TI. Okay, so let's do that. Again, there is no work involved, so work is going to be 0, but Q that the cooling water receives is equal to the Q that the steam is losing. So I'm going to change the sign for the Q and say 2406 m dot is equal to m dot of the cold water times 4.2 C of water times 35 minus 25 temperatures of water exiting and entering the tube. All I need to do is find the mass flow rate of the cooling water. So the mass flow rate of the cooling water can be found using the equation density, cross-section area, average velocity. So density of cooling water, we can approximate it with 1,000 kilograms per meters cubed, times the cross-section area. We know that the diameter of the pipe is 3 centimeters. So cross-section area will be pi times 0.03 over 2 squared times the average velocity, which is 2 meters per second. Now you do the math, you get that m dot of the cooling water is 1.41 kilograms per second. Okay, now I can plug this back into the green equation. So from the green equation, I know that m dot is 1.41 times 4.2 times 35 minus 25 over 2,406. M dot, which is the rate of condensation of steam, is 0.0246 kilograms per second. All right, problem 10. This is our first unsteady flow, so we are going to change our approach to the problems a bit. A rigid insulated tank is initially evacuated, and we have connected it through a valve to a supply line that carries steam at 4 megapascals. We open the valve and let the steam come into the tank until the pressure of the tank reaches 4 megapascals. If the temperature at this state inside the tank is 550 degrees Celsius, determine the temperature of the steam in the supply line. So let's start with the schematic of the problem. This is the pipe that we are dealing with, and it's connected with a valve to a tank like this. We are letting some steam entering the tank. We know that the supply line has a pressure of 4 megapascals, and we know at the final state the pressure inside the tank is 4 megapascals and the temperature is also 550 degrees Celsius. Now we are asked to find the temperature inside the supply line. So let's start with the conservation of mass. Now, conservation of mass states that whatever mass is coming in minus whatever mass is going out is equal to the change of mass of our control volume, which is mass 2 minus mass 1, if I take this as my control volume. Okay, now we know that initially the tank is empty, so M1, which is the initial mass, is 0. We also know that there is no mass going out of this tank, so MO is also 0. What we get is that whatever mass is entered is equal to our final mass. Okay, so keep this in mind. Now we can move to first law. Q dot net minus W dot net plus everything coming in minus everything going out is equal to the change of energy of our control volume, which can be written as mass 2 E2 minus mass 1 E1. Now, remember, theta, or the energy of a moving fluid, is enthalpy plus kinetic energy plus potential energy, and E, or the total energy of a system or substance control volume, is internal energy plus kinetic energy plus potential energy. We can ignore kinetic and potential energies. So theta reduces to enthalpy and E reduces to U. The tank is insulated, so that means there is no Q involved. And during the process, there is no work involved either. So work can be dropped as well. Also, we know that no mass is exiting. So this term drops, and we also know that the tank was empty initially, so this term drops as well. This equation is reduced to m dot I, h of I, is equal to m2 u2. Now remember that mi is equal to m2. I can drop these terms as well, and I get enthalpy of steam coming in is equal to the internal energy of steam at the final state. This is a very important conclusion. Now, h of I have no idea. I only know that the inlet has 4 megapascals of pressure. I don't know anything else. So there is no way for me to find h of I. U2, on the other hand, is something that I can work with. I know both the pressure and temperature at the final state. I can use the tables to find U2. So let's do that. Okay, so at the final state, I know that my pressure is 4 megapascals. My temperature is 550 degrees Celsius. Looking at the tables, you will instantly notice that we are dealing with a superheated steam. You will also notice that the temperature 550 is not provided in the tables. You will need to do a linear interpolation. The linear interpolation will be between the temperatures of 500 and 600. These are the temperatures that we have data for in the tables. So if you do the linear interpolation, you will get that the internal energy of the final states is 3189.85 kilojoules per kilogram. Now, from our first law conclusion, I know that the enthalpy at the entrance is equal to the internal energy of the second state. That means that the enthalpy at the entrance is 3189.85 kilojoules per kilogram. I need to check this data with the pressure of 4 megapascals. You'll notice that our enthalpy is greatly larger than the enthalpy of saturated vapor at the same pressure, 4 megapascals. So we are dealing with a superheated region. So let's go to the superheated steam and check with that. We'll see that the H that we have is larger than the H of 350 degrees Celsius and is smaller than the H of 400 degrees Celsius. So again, we don't see the exact number of the table. We need to do a linear interpolation. So the linear interpolation is between temperatures of 350 and 400 degrees. So that will be T minus 350 over H minus 3093.3 is equal to 400 minus 350 over 3214.3 minus 3093.3. Now keep in mind that I've done a detailed linear interpolation in a previous video. I'm going to post the link to that video in the description below and on the screen, on top of the screen right now. Make sure to check that video out if you have trouble with the linear interpolation concept. Now, if I plug H 3189.85 here, I can find the temperature I'm looking for. If I do that, I'll get that the temperature is 389.9 degrees Celsius. So I found the temperature of the supply line. Okay, problem 11. We have a 2 meters cube rigid tank that initially contains air at 100 kilopascals and 22 degrees Celsius. This tank is connected to a supply line. We open the valve and let the air come into the tank until the pressure inside the tank reaches the supply line, which is 600 kilopascals. At this moment, the temperature inside the tank is 77 degrees Celsius. We are asked to find the mass of air that entered and the amount of heat transfer. This is the pipe that we are dealing with. This is the tank. This is the valve. So supply line has a pressure of 600 kilopascals and a temperature of 22 degrees. And initially, the tank has pressure of 100 kilopascals and a temperature of 22 degrees. And finally, we have 600 kilopascals of pressure inside the tank, and the temperature is 77 degrees Celsius. So let's start with the conservation of mass. So conservation of mass states that mass coming in minus mass going out is equal to the change of mass of our control volume, which is M2 minus M1. If the red line here shows the boundaries of my control volume, no mass is exiting. So this term can be dropped. Mass coming in is equal to M2 minus M1. Now, let's see if I can find M1 and M2. In order to find M1 and M2, because we are dealing with an ideal gas, I'm going to use the ideal gas equation. So remember that P specific volume is RT. This is for an ideal gas, right? Now I can use the definition of a specific volume, total volume over mass, and plug it to ideal gas equation and get pressure, total volume is mass, gas constant, gas temperature. Again, playing with this equation, I get that the mass is pressure, total volume over gas constant, temperature. So this is the equation that I'm going to use. So initially, for M1, my system had a pressure of 100 kilopascals. The volume, the problem explicitly says that the volume is 2 meters cubed, so times 2 over the gas constant for air is 0.287. And the temperature, we need to put the temperature in Kelvin in ideal gas equation. So initial temperature is 22 degrees, which is 295 degrees Kelvin. This gives me 2.36 kilogram mass. For the final state, M2, again, I can use the same equation. Pressure is 600 kilopascals, volume is 2, R is 0.287. Temperature is 77 degrees Celsius, which is 350 Kelvin. Do the math, you get 11.94 kilograms. So the final mass is 11.94 kilograms. And the amount of mass entering is M2 minus M1, which is 11.94 minus 2.36. Mi is 9.58 kilograms. So this was part A. For part B, we are going to write down the first law. So Q net minus W net plus all the energy coming in with the flow minus all the energy going out with the flow is equal to the change of energy of our control volume, which we can write as M2 E2 minus M1 E1. Again, ignoring kinetic and potential energy, I get that theta is enthalpy and E is internal energy. During this process, there is no work done, so work is out. We know that there is no mass going out, so this guy's out. And we are looking for Q. So I have Q is equal to M2 U2 minus M1 U1 minus Mi HI. Now, you have two options here. You can either use the tables. There are property tables for air as an ideal gas at the end of nearly all thermodynamic textbooks, or you can approximate internal energy and enthalpy using these equations. Enthalpy of an ideal gas can be approximated by CPT of the gas. Internal energy of an ideal gas can be approximated by CV times temperature. Now, both these temperatures have to be in Kelvin. Just remember that. So I'm going to do just that. Now, Cp of air is about 1.005, and Cv of air is about 0.718, both kilojoules per kilogram Kelvin. So I'm going to use that. M2 from previous page, I know that it's 11.94. Now U2 can be approximated using CVT, which is 0.718 times the temperature, T2, which is 350, minus M1, 2.36, times, again, CV, 0.718, times the temperature T1, 295 Kelvin, minus mass coming in is 9.58 times Cp, 1.005, times the temperature of the supply line, which is 295 Kelvin. Now, if you do all the calculations, you get that Q net is minus 339.58 kilojoules, meaning that air is losing heat during this process. Okay, problem 12. We have an insulated vertical piston cylinder device. It initially has 10 kilograms of water, 6 kilograms of which is in vapor phase. So quality from the get-go, we know that the initial quality is 60%. The piston is applying a constant pressure of 200 kilopascals inside the cylinder. Now we are opening a valve to a supply line and letting some steam entering the piston until all the liquid inside the cylinder has vaporized. Now we are asked to find the final temperature and the mass of the steam that has entered. Okay, so just to have a visual reference, this is our problem. This is our piston and cylinder, and this is our supply line. This is the valve. So we know that the supply line has a pressure of 0.5 megapascals and a temperature of 350 degrees Celsius. And we also know that the entire process will be constant pressure. So what do we know? We know that at the initial state, we have quality of 60% and pressure of 200 kilopascals. We know that at the final state, everything has vaporized, so we are dealing with saturated vapor. And the pressure, because the process is constant pressure, is still 200 kilopascals. So part A asks for the final temperature in the cylinder. Now, we know that at final state, we are dealing with saturated vapor. The problem states that we close the valve as soon as everything inside the cylinder has evaporated. That means the state is saturated vapor. At that state, the temperature of the steam is equal to the saturation temperature of 200 kilopascals pressure. So T2 is the saturation temperature at P equal 200 kilopascals. And if we read from the tables, we'll see that that is 133.52 degrees Celsius. So that's part A. Now let's move to part B. We're asked to find the mass of steam that has entered. So let's start with the conservation of mass. Mass coming in minus mass going out is equal to second mass minus initial mass. Like previous problems, there is no mass going out, so this term can be dropped. The problem explicitly says that initially we have 10 kilograms, so M1 is 10 kilograms. So I get Mi is M2 minus 10. So let's leave it at that. Now we can go to the first law. Q net minus W net plus everything the flow brings in minus everything the flow takes out is equal to change of energy of our control volume. The system is insulated, so no Q. How about work? Now, so far, the problems that we dealt with, there were no work involved, but this time we are dealing with a piston that is able to move, meaning that the boundary is moving. Now we are letting steam coming into our system, so in order to keep the pressure constant, the piston has to expand. So the system is actually doing some boundary work. Now, what is the boundary work? Boundary work of a constant pressure system is pressure times specific volume 2 minus specific volume 1. So plug that in here. We get the boundary work. Because the system is actually doing work, we need a minus sign here. Minus the pressure, which is a constant, times specific volume 2 minus a specific volume 1. Plus, now again, we are ignoring potential and kinetic energies like this. So plus Mi Hi. No mass is going out, so this guy is 0, is equal to M2 U2 minus M1 U1. Now I need to find a specific volume final, specific volume initial, internal energy final, internal energy initial, and the enthalpy from the supply line. So let's start with the initial state. From the tables, I'm going to read both the specific volumes of saturated liquid and saturated vapor and internal energy of saturated liquid and saturated vapor. So V of F is 0.01061. V of G is 0.88578, both in meters cubed per kilogram. U of F is 504.5. U of FG is 2024.6 kilojoules, both kilojoules per kilogram. Now I can use the quality equation because I know that initially I have a quality of 60% to find the specific volume and internal energy at initial state. So specific volume 1 minus quality 1 times specific volume of saturated liquid plus quality 1 times specific volume of saturated vapor. Plug in numbers, you get 0.3189 meters cubed per kilogram. For U1, you have the equation U of F plus quality 1 U of Fg. plug in numbers, you get 1719.26 kilojoules per kilogram. I got everything I needed from the initial state. Let's go to the final and supply line. So at the second state, or the final state, I'm going to check the tables again for 200 kilopascals and saturated vapor. So U2 is U of G. From the tables, that is 2,529.1 kilojoules per kilogram. I also need specific volume, which is again specific volume of saturated vapor. From the tables, that is 0.88578 meters cubed per kilogram. Now at the inlet for the supply line, I have the pressure of 500 kilopascals and a temperature of 350 degrees Celsius, right? I check the tables and I find that we are dealing with superheated. So I jump to superheated tables, and for the pressure of 500 kilopascals and temperature of 350, enthalpy is 3,168.1 kilojoules per kilogram. I got everything. I just need to plug them back into my big equation. So I'm going to write that equation here again. Minus P1, specific volume 2 minus specific volume 1, plus MI HI. Now instead of M2, I'm going to plug in my conservation of mass conclusion. MI plus 10 times U2 minus M1 U1. Now plug in all the numbers that we have, you get minus 200.88578, 53189 plus MI 3,168.1 equal to MI plus 10 1 minus 10 times 1,719.26. Do the math. You get that the mass entered is 12.78 kilograms. So during this constant pressure process, about 13 kilograms of steam has entered this piston and cylinder. Okay, problem 13 is actually a rather easy one. It asks for the rate of evaporation of water if we are heating a water at 100 degrees Celsius with a heater of 3 kilowatts power. So a few problems back, we concluded that the Q, or the energy needed for phase change, at constant pressure is H of Fg. So with that in mind, I can say the rate of evaporation of water is the amount of energy or power provided divided by H of Fg at 100 degrees Celsius. That gives me 3 over H of Fg at 100 degrees Celsius. I need to read it from tables. 2,256.4, which is about 0.00133 kilograms per second. So remember, when phase change is happening at constant pressure, then H of Fg is the amount of heat needed for a phase change. Problem 14. The 4-liter pressure cooker has an operating pressure of 175 kilopascals. Now, initially, one half of the volume is filled with liquid and the other half with vapor. If it's desired that the pressure cooker not run out of liquid water for 1 hour, determine the highest rate of heat transfer allowed. So this is our cooker. This is the lid. We have a way here for steam to escape when the pressure inside exceeds 175 kilopascals. So the pressure inside is always 175 kilopascals. And the total volume is 4 liters. So first of all, let's see how much liquid mass we have in this cooker. I'm going to check the tables for the pressure of 175 kilopascals and read that the specific volume of saturated fluid is 0.001121 and saturated vapor is 0.21659, both in meters cubed per kilogram. Now the problem specifically states that half of the volume is filled with liquid. Okay, so I can say mass of fluid or mass of liquid is the volume occupied by the fluid over specific volume of the fluid. So that gives me 2 liters is 2 times 10 minus 3 meters cubed over 0.001121, which is 1.78 kilograms. We want this liquid to evaporate into vapor. We want it to happen in 1 hour. So the rate of evaporation, m dot of evaporation, is 1.78 kilograms over 1 hour, which is 3,600 seconds. This gives me 4.95 times 10 to minus 4 kilograms per second. So this is the rate of evaporation. Now, why I'm calculating the rate of evaporation? Because I'm going to use the conclusion of previous problem to solve this one. We want to boil water. That's all we want to do. We have 1.78 kilograms of water, and we want it to evaporate with the rate of 4.95 times 10 to minus 4 kilograms per second. So the amount of Q that we need is m dot times h of Fg. Now, h of Fg you can read from the tables at the pressure of 175 kilopascals. The value is 2031.7. We get that Q dot is 4.95 times 10 to minus 4 times 2031.7, which is about 1 kilowatts. Here I use the conclusion of previous problem, knowing that the rate of evaporation is dependent on the h of Fg at the constant pressure. But there is another way. We know that during this process, when water is boiling, some water escapes the cooker to keep the pressure at 175 kilopascal. Now we can treat this as a normal control volume problem where some mass is escaping, and then write down the conservation of mass, write down the first law, and find out that the amount of Q allowed is 1 kilowatt. Actually, I strongly suggest that you try to solve the problem the other way as well, just to see that both approaches will give you the same result. Problem 15. We have a balloon that has a volume of 65 meters cubed, and it's filled with helium gas. The initial state of the helium inside the balloon is 100 kilopascals pressure and 22 degrees Celsius temperature. This balloon is connected to a supply line. We are going to open it and let the helium flow into the balloon until the pressure reaches 150 kilopascals. This balloon has a very specific material. such that the volume increases linearly with the pressure. If no heat transfer takes place during this process, determine the final pressure inside the balloon. So we've got a balloon like this, and it's connected to a supply line. Initially, this balloon has a pressure of 100 kilopascals and 22 degrees Celsius temperature, okay? At the final state, it reaches the pressure of 150 kilopascals, and the temperature is unknown. Now, during this process, the size of the balloon has increased to a new number, okay? Let's see what we have at each state. We know that initially, pressure 1 is 100 kilopascals, temperature 1 is 22 degrees. We know that finally, pressure is 150, temperature is unknown, and we know that the supply line is 150 kilopascals and the temperature is 25. Okay, so let's start with the conservation of mass. Conservation of mass says that mass coming in minus mass going out is the mass of the final state minus mass of initial state. There is no mass going out, so this is 0, and I get mass coming in is the second mass minus initial mass, right? Now let's see if we can find some numbers for these masses. Ideal gas equation says that P, specific volume, is RT. Playing with this equation, I get P, total volume, is mass RT. Again, playing with this equation, I get that mass is P, total volume, over RT. So initially, the mass of helium inside is 100 kilopascals times total volume, 65 meters cubed, over the gas constant for helium, we can read it from tables, is 2.0769. Cp of helium is 5.1926, and Cv of helium is 3.1156, all three in kilojoules per kilogram Kelvin. So I'm going to plug in the gas constant here, 2.0769 times the initial temperature is 22 degrees, which in kelvins is 295. This gives me 10.61 kilograms. So 10.61 kilograms of helium was in the balloon initially. Now, how about the final state? At the final state, we need to pay attention to one thing. It says that the volume of the balloon increases linearly with the pressure. So the final volume is P2 over P1 initial volume. If we plug in numbers, I get 150 over 100 times 65. This gives me 97.5 meters cubed. So I found the final volume. Now, mass of the final state is P2 volume 2 over RT2, which gives me 150 times 97.5 over 2.0769 times T2, which is our unknown. So that's for the second mass. Now that we are done with the conservation of mass, we need to follow up with the conservation of energy, or first law. So let's write down the first law. We get Q minus W plus the energy that the flow brings in minus the energy that the flow takes out is equal to the change of energy of our control volume. No mass is going out, so this term is dropped. The problem again explicitly says that there is no heat transfer involved, so Q is gone. What about work? Now we know that this balloon is expanding in volume. It means that the boundaries of the control volume is moving. So we have boundary work. Now remember, whenever we had a situation where pressure and volume had a linear relationship, we could use the plots to find the boundary work. Let me show it on this PV diagram. So if this is P and if this is volume, initially we had the pressure of 100 kilopascals and a volume of 65 meters cubed. Finally, we have a volume of 92.5 and a pressure of 150. This is the process, right? The boundary work is the area under this curve. This is the boundary work. So what is that? Boundary work is 1/2 of 100 plus 150 times 92.5 minus 65, which is 3,437.5 kilojoules. So we found the boundary work using our knowledge of the process. Now the system is expanding. It means that the system is doing work, so the sign will be negative. Also, from the conservation of mass, we know that m of I is m2 minus m1. So let's plug these things back into our first law equation. So I get minus boundary work plus m2 minus m1 times hi, supply line, enthalpy of the supply line, is equal to m2 u2 minus m1 u1. Now also, I know that m2 had a relation with T2. It's 150 times 97.5 over 2.0769 times T2. Okay, so let's combine everything together. Okay, so I cleared the calculation space and moved everything up here. Now, if I plug in numbers, I get minus 3,437.5 plus 150 times 97.5 over 2.0769 times T2 minus M1 is 10.61. Now for the enthalpy of the supply line, I can approximate it using this equation. H is approximately CPT. Also, internal energy is approximately CVT. So with that in mind, H of I is Cp of helium, 5.1926 times the temperature of the supply line in Kelvin. Remember, when using these equations, temperature has to be in Kelvin. So the temperature of the supply line is 25 degrees, which is 298 Kelvin, is equal to M2, again, is 150 times 97.5 over 2.0769 times unknown T2 times U2, which is Cv of helium, 3.1156 times the temperature T2 minus M1 is 1061 times Cv of helium, 3.1156 times temperature T1, which is 22 degrees Celsius in Kelvin, that is 295. Now we have an equation where T2 is the only unknown. Playing with this equation and doing the calculations, you get that the T2 or the final temperature, is 333.55 Kelvin. So in this problem, we kind of reviewed everything that we learned in this thermodynamic course so far. First, there was a linear relation between the volume and the pressure. We used that to find the second or final volume. Then we used the ideal gas equation to find the mass at the initial and final state. For the final state, we needed temperature to find the mass. Then we used the first law equation for the boundary work because the volume had changed and we needed to find the boundary work. This was a process at which volume and pressure had a linear relation. So we used that to our advantage. I drew the process on a PV diagram and then calculated the area underneath. Because the system was expanding, it meant that the system was actually doing work. That's why I used a negative sign for the boundary work. Then, in order to approximate enthalpy and internal energy for our ideal gas, we used these equations that relate the enthalpy and internal energy to their absolute temperatures, and then plugged in everything back into the first law equation and did some calculations, and I found the unknown temperature. Thank you for staying to the end of yet another video. If you find this video helpful, please give it a like as it greatly helps the channel. Also, please consider subscribing for more science and engineering content. Thanks again and see you in another video.